who's here in person to sunny Arizona, given that it rained this morning. I'm Phil Mauskopf. I'm from Arizona as well, but from up the road at Arizona State University, and I'll be talking to you today about something that Avi introduced, the Starshot, Breakthrough Starshot project, and my role, and I'll be talking about the communications challenge for exploration of nearby stars and star systems with low mass probes. So this is relevant and has been kicked off by this Breakthrough Starshot mission. So Avi gave an introduction in the middle of his talk, which was great. So I can go through this quickly. And then also later today, Pete Warden will be giving another overview of the mission as a whole. But just to remind or to set the stage for the rest of my talk, I'll just summarize that the mission currently is planned to send light sails to the Centauri system, as Avi mentioned, cruising at 20% the speed of light. And the launch system now, I suppose, with some of the other talks that we've had here today, sounds somewhat mundane, but it's using a ground-based laser array beaming light sails and accelerating them. So this is the concept of operations, as you saw in the video earlier, is that there's a launch of the light sails into low Earth orbit or Earth orbit, and then acceleration by the laser, and then cruising to the Centauri star system for 20 years, and then obtaining some images of planets and relaying the data back to us. So what I'll talk about today is some of the challenges in that last part, which is how do we get the data back from such a probe. The main goal of the Starshot mission is to send back from each probe an image or similar type data of the system, and rough numbers are about 100 kilobytes of information. The current technology for sending this type of information is radio communications. That's what has been used for many years in space missions exploring our own solar system. There is now next generation technology, which will be using laser optical communications. So I'll talk about how do we go from where we are today to where we need to be. There are many unsolved problems in this whole mission, including how do we get the power? What is the power source? Various people have been talking about that. How do we do the navigation? How do we acquire the images? But I'll just be focusing on how do we send the image data back once we get it. So one example of current or fairly recent technology, and again, I know I'm aware I'm doing shout outs to a lot of people who are here at this meeting, which is great. So we heard from Alan Stern, who was the PI for the NASA New Horizons mission. So I'm using this as an example of a fairly distant fairly recent communication system, sending the data back from the Pluto flyby and beyond. And so most of the data that we've received from this mission has been sent with a 12-watt X-band transmitter with an onboard 2-meter Cassegrain antenna. The total weight budget for this is tens of kilograms. So the important factors are power and weight for us. And so 10 watts or so and tens of kilograms. And just because they look nice, here's an example of what you can get with that from the outer solar system. You can get images like this of, this is Pluto's moon, Charon, and this is at a distance from the Earth of approximately 30 AUs or 0.0005 light years. The downlink rate that you have for this type of image is about 1 kilobit per second. And it's downlinked to the NASA Deep Space Network dishes on the ground. And it takes it at this rate to downlink all this data, or there were approximately 6 gigabytes of data that were downlinked in the course of a year after the flyby. So for Starshot, what we're looking at is we would like to get images of whatever planets and bodies are in the star system. The speed, of course, that we're traveling is 0.2c. That's a challenge, obviously, for acquiring images. But the main challenge for downlinking the images, of course, is the great distance. So we're at 4 light years away. The downlink rate that we are targeting is approximately, so it can cover a wide range, but I've put approximately 0.1 to 10 bits per second, depending on the method. And the time to downlink at least one image from a particular probe flyby, again, we would like for that to be on the timescale of, similar timescale to New Horizons of about a year. And so the question is, how much harder is this than the current state of the art, and how are we going to get there? So how are we going to achieve this? And so just an overview of the parameters, you can compare weight and power, and then what are some of the other important parameters for such a communication system. And so obviously the two of the big challenges are that we are trying to not only scale in distance, and so the distance makes the transmitter data rate much more difficult, but we're also scaling in weight and in power. So for example, we want to scale from the tens of kilograms of New Horizons down to approximately 1 gram in order to be able to accelerate this on a light sail to that speed. And the transmit power, we're severely limited. So instead of say on order 10 watts, we're looking at less than or so tens of milliwatts of power. And so, but on the other side, we are not quite as ambitious in how much data we need from each probe. So 100 kilobytes versus 6 gigabytes. So if you combine these into figures of merit, you can make a figure of merit, which is the transmit sort of efficiency of your system. This is a figure of merit that is different from, say, the link budget, which is a standard communications figure of merit. This one takes into account the weight and the power. And so I've just calculated this in kilobits per second per distance squared, and then per kilogram or per watt. And this is in order to compare what the goals are for the Starshot communication system with, what is the current state of the art. And as you can see, the current state of the art, if you calculate the figure of merits for weight or for or data rate per watt per distance squared or data rate per kilogram per distance squared, are on the order of tens to 100 in these units. For Starshot, we need to increase this or improve this by about eight or 9 orders of magnitude. So that's the level of the challenge. We have some time, but that's still a lot of orders of magnitude. So one way of doing this is to go to laser communications. That should get you better data rates. An example of this is the NASA's Deep Space Optical Communication System, which will fly on the NASA Psyche mission, which is led by PI Lindy Elkins-Tanton, who's at Arizona State University as well. This system has been developed at JPL and will be the first deep space laser comm system scheduled for launch in the next year. So that's very exciting. So what does this get you? If you use the parameters for the DSOC published in their paper in Nature Astronomy, you get roughly 1 order of magnitude, 1 to 2 orders of magnitude improvement over in these figures of merit. So per weight or per mass or per power over the radio system. However, if you instead calculate from first principles, and so another shout out here is going to Dave Messerschmidt, Phil Lube, and Ian Morrison, who are either in attendance virtually or in person, at least some of them, for some of their papers that they've written on this. You can parameterize the communications data rates in terms of some number of physical parameters of your system. And if you do that and you calculate what is the data rate? I'm going to go through these equations quickly. You actually get that that the deep space optical comm system should be much more capable than they are claiming that it will be in the Nature paper by about 2 orders of magnitude. And so if you then include that, you can summarize, okay, how are we going to go from, say, the current state of the art, which is deep space optical communication system, to what is required for Starshot. And so I have in this table that we require approximately 7 orders of magnitude improvement over the deep space optical comms. And I've summarized now 4 different areas where we might gain some of these orders of magnitude. One of them is in what I'm calling the number of bits per photon, or it's really just a calculation of, what is the optimum data rate that you could get for a system with a certain physical parameters. And so I'm saying, well, even if we don't do very much, we might be able to gain, 1 to 3 orders of magnitude, or 1 to 2 orders of magnitude over the published deep space optical communications data rate. Another area is the effective collecting area on the ground. So the Deep Space Optical Communication System is planning on using the Palomar 5-meter diameter telescope as its ground station. So that has, some amount of area, surface area. Obviously, we have a lot of time before we have to actually receive the data. So you could imagine building a really large collecting area on the ground, sort of square kilometers or so. And this will gain you maybe up to 4 or 5 orders of magnitude in terms of your ability to collect photons from the transmitter on board. And then the other ways that we can gain are if we could possibly use the entire diameter, say, of the light sail, or a large fraction of it, then we could increase the effective diameter of the transmit aperture over DSOC by maybe up to 1 order of magnitude, so gaining a few orders of magnitude there. If you add these up, so these are things that we have to investigate and figure out how to do in practice, then it is theoretically possible to get this increase in the transmit order data rate that we require. One of the challenges that's not specifically addressed here is how do we do this and at the same time decrease the mass on board that's required, and that is a very big challenge. So in order to try and move forward and achieve some of these increases, the Breakthrough Starshot project has issued and has started an R&D effort to investigate ways of moving from the current state of the art into the requirements for the Breakthrough Starshot project for communications. This is called the Phase 1 R&D. There are 3 goals. They're listed here. The goals are to develop and refine theoretical concepts, system designs for doing this, design and develop subsystem components for the onboard transmit system, and design and develop subsystem components for a ground receiving station. And this was issued, this call for proposals was issued at the end of and beginning of this year, end of last year, and we received proposals, and now we have selected these groups. They're Phase 1 groups. They're from all over the world, including a group here at the University of Arizona, and work is just starting. So we have a number of groups. These are the summary of the groups and their topics. And so we had the status of this effort is that we had a pre-Phase 1 workshop in April 2020. This was hosted by the Interplanetary Initiative at ASU, which is led by Lindy Elkins-Tanton, who's PI of Psyche. And this was on Zoom. We had over 80 people attending from all over the world, and there's a report from the workshop with slides, models, and these are all available at this webpage at www.starshotasu.com. And then, as I said, we've selected the teams that are going to do Phase 1 research. There was a Phase 1 kickoff meeting just a few weeks ago, September 11th. And so work is now starting. Teams are starting to ramp up. This work and these efforts have potential synergies with lots of things: NASA research, commercial space, security, other communication systems. And so we're very excited about the opportunities and the possibilities. And so hopefully there should be lots of results coming out soon. So that's all. So I'll end there. Thank you very much.
That's great. We've got time for a few questions. I want to remind the people in the room, we're collecting questions on these little squares of paper. So either bring them over here to Dennis or over to Doug at the far end. If you need more paper, we've got more. If you're on the Zoom channel, make sure you get the question where Dennis can see it. And I think you've got one to start with, right?
Yes, we got one. So rather than using them for radio astronomy, could a large antenna on the far side of the moon improve deep space communication capability? And is anyone proposing this?
Yes, so we are not currently studying that in the phase 1 Starshot effort at the moment. I would say that the potential advantages of doing this on the moon could be that, yeah, if you're communicating at radio frequencies where there's a lot of interference on the Earth, then that would certainly be a big advantage. If you're communicating in the optical, though, if we're doing laser communication, there are some advantages. It's, you don't have any atmosphere, so there's no loss of optical photons through the atmosphere. However, the disadvantages are clearly that constructing, a square kilometer array of optical receivers on the moon is probably a little bit more expensive than doing that on the ground.
Thank you. How can a light sail be used as a laser emitter?
Right, so I think there's two main ways that people are starting to study this. One is by the fact that the light sail is designed to be reflective because it needs to reflect the beam on launch. And so if you can use some sort of technology to control the surface when it's after it's passed through the star system, then you can use it as a reflector to reflect and focus a beam back towards the Earth. The other thing that's being studied is incorporating into the light sail arrays, say, of a phased array of laser emitters, so that you can use the light sail itself and have little lasers interspersed in the actual material of the sail, and then coherently combine them in order to direct that energy towards the Earth, almost like a miniature beamer on the light sail itself, but obviously with strong constraints on mass and power.
Thank you. Could you improve the order of magnitude capability by using more exotic means of communication like quantum communication or things like this?
So there are several groups actually studying how to improve say the number of modes, or to use quantum information in order to improve the communication efficiency. This includes studying things like squeezing and also entangling, if that is a possibility. There are ways of doing this, but so far it appears that sort of gains are modest. In other words, not orders of magnitude, but maybe one order of magnitude.
Thank you. And finally, are you considering multiple modulation methods to increase bits per photon? For example, polarization, frequency, etc.
Yes. So again, there are groups studying those topics. There's polarization. There's a couple of groups that are interested in orbital angular momentum in terms of increasing the number of modes. But yeah, and then there are groups just studying the different modulation schemes in order to maximize the information. Anyway, so I thank you all. This was great, and I'm amazed that I was not called for time in the middle of my talk. So I'm glad
you're good. You're good. Thanks very much.